Welcome to The Explainer. Let's jump right in. Today, we're diving into what I honestly consider the ultimate scientific mystery.
Think about it. How do you count what you can't even see? Atoms and molecules are so incredibly tiny, right? You can't see them with your naked eye, not even with a standard microscope. But here's the catch. Knowing exactly how many are reacting is literally the entire basis of modern chemistry. It's like a giant invisible puzzle. So, to solve this mystery, here's our roadmap for today. We'll cover the scope of chemistry, the laws of chemical combination, the building blocks of matter, the international system, and finally, we'll unlock the mole concept.
Okay, Section 1. The scope of chemistry, from the macro world down to our everyday life. You know, chemistry gets called the central science for a really good reason. I mean, look at what it touches. Health, energy, the environment, materials, agriculture. We're talking about everything from mapping human genes and developing vaccines to making solar cells and even room temperature superconductors that conduct electricity with zero energy loss. It is absolutely crucial. It's literally the foundation of our future.
Moving on to Section 2. Laws of chemical combination, the rules of the physical game.
So to understand those rules, we've got to look back. The idea of the atom actually isn't new at all. Way back around 500 BC, Maharishi Kanad proposed the Parmanu, and Democritus proposed the indivisible atom right around the same time. But here's the wild part. For over 2 millennia, these tiny particles were just pure philosophy. It wasn't until the 19th century that scientists finally started using the chemical balance to accurately measure reactions.
And the guy who really cracked the code? French chemist Antoine Lavoisier. He did this incredible experiment where he heated mercury in a sealed flask containing air, which produced a red substance called mercury 2 oxide. Then he heated it even stronger to decompose it back into mercury and oxygen. And here's the absolute magic of it. The combined mass of the products precisely equaled the original mass. Boom! This definitively proved the law of conservation of mass. In every single chemical reaction, the total mass of the reactants always equals the total mass of the products.
That massive breakthrough paved the way for even more rules. You had Proust's law of definite proportions, which showed that pure water is always, and I mean always, 1 part hydrogen to 8 parts oxygen by mass, no matter where you get it. Then Dalton's law of multiple proportions proved that when elements form more than one compound, like carbon monoxide versus carbon dioxide, they always do so in a ratio of small whole numbers. So what does this all mean? It means matter isn't just random chaos. It follows a strict, unchangeable mathematical recipe.
Then along comes British chemist John Dalton. He took all these precise measurements and brilliantly wrapped them up into 5 main postulates. He proposed that matter consists of these indestructible, indivisible atoms, and that compounds form when they combine in those small whole number ratios. This finally gave scientists a real functional framework for how atoms actually work.
All right, Section 3. Building blocks of matter. The players on the microscopic stage.
Let's define exactly who these tiny players are. An atom is the smallest particle of an element that still retains its chemical properties. Now, sure, modern physics can break them down even further into subatomic particles, but doing that strips away their unique chemical identity. Because of that, the atom remains our true, fundamental building block.
And when we look at how they combine, we've got to differentiate between elements and molecules. Elements are your pure substances. There are 118 identified basic ingredients that simply cannot be chemically separated into anything simpler. Think hydrogen or oxygen. Molecules, on the other hand, are the independent structures that form when at least 2 of those atoms bond together. They can be diatomic, like H2, or polyatomic, like water, H2O.
To keep track of the whole shebang, chemists use standardized symbols. Now, some are super intuitive, like C for carbon. Easy, right? But a lot of them are actually remnants of their old Latin names. That's why gold is Au from aurum, iron is Fe from ferrum, and sodium, well, sodium is represented by Na because of the Latin word natrium. Kinda cool, right?
Moving to Section 4, the International System, or SI, the language of measurement.
Historically, having different countries using completely different units created absolute scientific chaos. So, in 1960, the world got together and adopted the International System of Units. It's based on 7 fundamental base quantities. From the meter for length to the Kelvin for temperature, this system allows scientists across the globe to measure the physical world perfectly without anything getting lost in translation.
And finally, Section 5, Unlocking the Mole Concept, Counting by Weighing.
Okay, did you happen to catch that 6th SI unit on the last list? The amount of substance? That right there is the key to our initial mystery. To understand it, just imagine you need exactly 500 tiny screws at a hardware store, or imagine a bank dealing with massive piles of coins. You're definitely not going to stand there and count them out one by one, right? No way!
Instead, you'd do something way smarter. You'd weigh a single screw. Let's say it's 0.8 grams. Then you calculate the total mass of 500 screws. So 0.8 grams times 500 gives you 400 grams. Then you just scoop and weigh out exactly 400 grams of screws. You're using the brilliant shortcut of counting by weighing, using the mass of an object to instantly figure out the quantity. And you guys, this is exactly the logic chemists use to count atoms.
Since atoms combine in specific number ratios rather than mass ratios, chemists created the mole. It's defined as the amount of a substance containing as many elementary entities as there are atoms in exactly 12 grams of the carbon-12 isotope. Basically, the mole is a massive number unit. It directly links the physical mass of a substance to the exact number of invisible particles inside of it. And the term itself, coined by chemist Wilhelm Ostwald, is actually pretty literal. Mole comes from the Latin word molus, which literally means a heap or a pile. So just like the word dozen means a pile of 12, a mole just means a specific, really large pile of particles. But how big is that pile? Well, it is astronomically large. We're talking 6.022 times 10 to the 23rd power. This is known as Avogadro's constant. What it means is that 1 mole of any substance will always contain exactly that many particles.
This concept is a real game changer. It acts as the ultimate translator between the visible world and the invisible one. As it's often taught, with the help of the mole concept, it is possible to take a desired number of atoms or molecules simply by weighing them. It beautifully bridges the gap between the physical mass you read on a scale and the microscopic quantities reacting in the flask.
So the crucial takeaway here is that our universe isn't just some random chaos. It's a perfectly measurable equation. Knowing that even a single tiny speck of dust contains 10 quadrillion molecules, what invisible world will you calculate next? The rules of chemical arithmetic are out there, literally waiting for you to weigh them. Thanks for joining me on this explainer, and keep exploring.